that and you look at a circuit board, it's like, what does all this do and how can I even do anything interesting with it? And I kind of fell into this project and it was really easy and really cool, and so I thought I'd share it. So what we're going to do is I'm going to talk to you how I kind of bought one of these cheap Rfid lock sets off of eBay. They're about $12 or $15, $12 you buy now. It's kind of standalone. I'm going to pass this around. It's already broken, so break more. That's just fine. It's got tiny little wires holding the board to the antenna, and if those aren't broken by the time it gets back to me, I'm very disappointed in you guys. So yeah, $12 gets the RFID keys and all that. And I bought this after we were using our Proxmark at a demo that we were doing. It was really hard to use the Proxmark, like the candy feather antennas, and bought this thing and got it over like, oh, this board actually looks kind of simple. So that's kind of the first step of kind of hardware hacking, just looking at the board. When you first look at it, you've never been in there before, it's like, what are all these things on here? What do they do? And I'm going to talk through some of those. So the first thing I saw on there, because most boards have it, and I recognize it right away as a voltage regulator. That's a component, it's this little square thing there. You can see there's printing on it. The one on the board in the green there, it says 78M05. So most part numbers have standard manufacturer, or have a part number on them. If they're made by many manufacturers, a lot of times they'll have the same part number across different manufacturers. So for that, just that one component, I can go on the web, find the data sheet. Don't be afraid of data sheets. They look a little daunting, but if you spend a little time looking at it, you start to understand. And I went right to the electrical characteristics, and I'm interested, okay, the output voltage on that is 5 volts. So that tells us something interesting. Even though the input on the board itself says it requires 12 volts, the circuitry, the computer circuitry on there is most likely using a 5 volt power supply, so I want to use 5 volt, want to look for 5 volt signals or partial 5 volt signals or things like that. The other thing I can see from the data sheet here is the VI for that 5 volts is actually 7 to 20 volts. So I don't need to use 12 volts. I could use a 9 volt battery to power the board, and the board itself would still get the 5 volts if I can use anything down to 7 volts. It's likely they require 12 volts because they use the same feed to feed like the lock sets, and I assume those door lock sets run on 12 volt DC. But if I'm not actually running a lock, I just want a light on the lock, not where the lock would be like an LED. A 9 volt battery, that would be fine. So even just that one little component, I can learn some interesting things. It's 5 volt, I don't need to use 12 volt, I can use a 9 volt power supply if I've got it, things like that. So that's a bit about data sheets. I'm going kind of fast because I got a lot of slides. Next thing I saw was this big chip in the middle of the microprocessor. I never heard of DerbyCon before, got a big long part number. I looked it up and just kind of looked through the preamble on the data sheet. I see it's an 8051. That's something I've heard before, but I've never programmed it. But maybe I can figure out how. I program Arduino, and that's about it from a microcontroller standpoint. But it's got RAM on board and all that. And then I get down to the bottom, and it says, "Oh, it allows the programmers." Should have done that. Allows the program memory to be read. Like, well, that's cool. Maybe I can actually read off the memory, start tampering with it, and catch the signal that it's seeing or whatever. And then I see the next line that says, once the code is confirmed, there's security. Okay, so maybe I can't enter the code. I'll put that aside for later. But I at least know a little bit about the chip and things like that at this point. And the data sheet actually says what each pin on it is for, and I can start tracing the pins to where they go. I didn't really do much of that. Looked around the board some more. You'll see a lot of integrated circuits. You can look up the data sheets for those. This one's just a hex inverter. I don't know what it does. It's not very interesting to me. Moved on. Here's another chip on the board, a little memory chip. So it looks like a 32K memory, that 24HC32. Again, I can pull up the data sheet for it. That's something I can likely read or write. But I'm thinking about, okay, my goal is to have someone swipe a card and I want to intercept their number. Well, it's not likely when someone swipes a card that the processor is going to send the card to memory. It's going to read cards from memory maybe, so maybe that's something else. But at this point, I was just trying to find a way that someone's going to, swipe a card. I can grab their ID when they swipe it. Other things on the board, capacitors you're kind of familiar with. What are they used for, really? So you see these big round ones up in the top corner. Those are on the board. They're right near the power input. I'm assuming they're just for power conditioning. So they store a little extra charge, and as different components use different charges, it kind of keeps it even. And then you see the same thing right here next to that hex inverter that we saw. This C13 on the second picture is another capacitor. It's connected right to the power pin of that one. And again, it's right next to the component, but it's still doing power conditioning. So there's just a constant, 5-volt voltage going into that, and that capacitor just kind of keeping that even. And then finally, especially for an RF circuit like this, capacitors are used, in conjunction with an inductor. An inductor is just coil wire. So you take a coil wire and capacitor, put them together, and you've got a circuit that will resonate at a certain frequency. And that's what we see on the bottom here. The two little tiny wires on the bottom are the antenna coil that goes around the board. And then the green thing here is another capacitor that's on that circuit, so I assume it's helping that resonate. Resistors, there's resistors all over the board. They're used for lots of different things. So voltage dividers, the way a resistor typically does is it drops the voltage. If you use two of them, like the picture on the side, V out is going to be some partial percentage of what V in is, so you can reduce your voltage. Often you'll see them for protection, so if you've got input signals, you'll put kind of low value resistors on that, so that if someone puts a higher voltage on it, it should be or something like that, it's going to limit the current that goes into your chip. They're used for pull-ups and pull-downs a lot. When I started playing with kind of hardware hacking like this, I saw that people who know what they're talking about use that term a lot, but had a really hard time finding someone describing well what it meant. And so I got stuck on that for some days or longer. But pull-ups and pull-downs, the way it works, so you guys are probably familiar with kind of the Arduino card here. It's got input pins where you can input a signal. And your input signal is either, if I stuck a wire onto one of those input pins, I can touch to ground and that's going to mean a 0, or I can touch it to positive voltage and that's going to mean a 1. So 0, 1, 0, 1. But if I just leave that wire hanging out here, anybody know what that'll read on the Arduino? It's random, it reads whatever, there's no signal, but it will read a 0 or 1, it's got to read something. That's where pull-ups or pull-downs come in. In addition to that wire that I'm not touching to anything, I would have a resistor going to either ground for a pull-down or going to positive voltage for a pull-up. And if that wire's not touching anything, that pin is going to be whatever signal that resistor is connected to. So it's going to be a 0 if I've got it pulled down, it's going to be 1 if I've got it pulled up. But then when I go and touch this to something, then it's going to be whatever I touch it to, because the resistance in my wire is much less than that resistor. So the wire takes precedence at that point. If I touch the voltage, now it becomes a 1. If I touch the ground, it still stays a ground. So they're important to know about, especially when you're starting to build circuits with the Arduino, to know, okay, am I actually getting a signal in there, or are there times that I'm not getting a signal, but I'm reading a signal? If that's the case, you want to add a pull-up or a pull-down to give it kind of default. You always want it to be 0 unless it touches the positive, or you always want it to be 1 unless you touch the ground. So that's pull-ups and pull-downs. Here's just a quick picture of some surface mount resistors. I'm guessing these are pull-ups or pull-downs because they're kind of an array and they're near the push buttons. So when the button's not pushed, it's probably pulled down, and when they push the button, it's going to bring the signal up. Very simple little yellow relay on there. All that is the switch that the logic from the processor can turn this kind of, it's actually a physical switch in there. You can hear it click. When you turn it on or off, you'll hear the solenoid there click on or off. And that tiny little component is, size of my thumb tip, but apparently it's a 250 volt AC component even, so that was interesting to me. Diodes all over the board. I've never really had to deal with what is this diode doing when I've been doing this stuff. I know they're used to make sure current only flows one direction to protect things. There's clamp diodes that make sure you can't enter, or only a certain voltage will go through a circuit, other ones will be clamped off the ground or whatever. And your LEDs are diodes as well. Not really interesting from a logic perspective. There's a little crystal on there. You see that on almost every board. It's just a little piece of quartz or something that oscillates to create your signal. I can see that this one's 12 megahertz. That's a little interesting because I just want to know, okay, what is the clock cycle of that processor? My Arduino, I think, is 80 megahertz. Someone can correct me if I'm wrong. So my Arduino is faster than that. Well, that's something good for me because then if I'm going to write code in the Arduino, it's going to be at least as fast as the processor that's in there that's running at 12 megahertz. Again, I have no electrical engineering background. A lot of what I say is probably crap, and people can call me out on that, that's fine. I learned as I went, and that's what I kind of want to share with people. Transistors. So this is the 3-pin part that you basically, current flows through it, but the 3rd pin on it tells the current whether or not to flow. And it can let some flow or all flow through. They can do it based on voltage on that kind of, they call it the gate pin or the current on the gate pin. But just basically, really often in these electronic circuits, they're used to switches. We can see these little black things towards the top of the picture there are 2 transistors. I'm assuming, I didn't look that close, but I'm pretty sure they are, that are turning those LEDs on or off. So you're not feeding current right to the LED from the processor, from the chip. You're feeding a signal from the chip to that transistor that tells that transistor, turn that flow on or turn that flow off. And that way you're not feeding a lot of current through your chip, through your processor chip. So, first tool I used, a multi-tester. You definitely need a multi-tester. Even if you're not going to need a multi-tester, I don't know how anybody would get away without having one. This is the one I use. It's $5 at Harbor Freight Tools, if you're lucky enough to have a Harbor Freight Tools nearby. I like $5 Harbor Freight Tools because I burn them out a lot by doing stupid things. If you're smart, you won't burn them out, but if you get stressed out by the contractor who's trying to work outside your house on something, like the circuit's down, so without flipping the right things, you just put it in the outlet and burn it out, and smoke rises. Yeah, I got a lot of these kind of scorched, fun. So I don't buy expensive ones. Actually, that's kind of the theme behind a lot of this. It's similar to being a owner. I don't have the funds to do expensive projects where I'm going to break things, and that's what's nice about this. The lock itself is $12. Our windows are pretty cheap. So better equipment is definitely better, but cheaper actually lets me get the foot in the door. So the first thing I did then was kind of power it on and okay, what's interesting? I bet there's signals on this chip. And actually I was hoping it would be, for some reason, outputting the code that I read out on a pin of the chip, and I didn't really find anything that was doing that. The actual code, like the number that's on the card. But what I did find is that one of these pins, pin 16, on the chip, shows 2.9 volts, which it's interesting because if you're doing all the pins, and pretty much that one's a ground, it's 0 volts, 0 volts, 5 volts, 5 volts, 0 volts, which pretty much tells you it's either kind of a pin that's just setting that this is high and then something, or this is low, or there's not really a lot going on. But here seeing a 2.9 volts, there's a good chance that there's actually a data signal on that pin. When my multi-tester is averaging, when the signal is high at 5 volts and the signal is low at 0 volts, down to some average that's 2.9. So that's an interesting pin, and probably other ones as well. So I want to know more about it. It's probably the most expensive component I have. I'd love to get an oscilloscope. I don't have one. Maybe now that I've got a few extra bucks from selling a couple things here, I can buy one. But what I do have is this really cheap logic analyzer. I got it for like 40 bucks off of eBay. It's a knockoff of the Sela brand. But basically what it does, it's like an oscilloscope where it's measuring signals, but it only measures whether it's a 0 or 1. It doesn't measure the actual analog. It's just up, down, up, down, up, down. Whoops. What happened here? What the heck? Yeah. Sorry about that. Here. All right. So, we're going to use the logic analyzer in a second, but I want to talk about grounding because this is another place I kind of got stuck. So you always forget, kind of, if I've got 2 boards, whether it's Arduino or another board, or the logic analyzer or another board, or 2 boards that are trying to talk to each other, they need to have a common ground. You think, like, do they connect the grounds together? They're both running off a different power supply or something. Yes, you connect the grounds together in any case that I've come across anyway. And the reason for that is, if this board is sending a signal to this board, it's sending voltage compared to ground. And each board probably has a different sense of what ground is. If you check the voltage across both grounds, you'd see that it was not 0 volts, there was something there. You connect them together, they both decide, okay, we're going to share this common ground, and whatever's not that ground is a signal I can understand. So one of the things that took me a little while, and I always kind of thought, why aren't I getting a good signal? Oh, I forgot the ground board that I'm looking at or whatever. So you gotta connect the grounds together. And so what I've actually got here is that board, and I've soldered onto, or I've clamped, So I clamped onto the ground pin, ground pin on that chip, and pin 16 on that chip. And I'm going to launch my logic analyzer. And it's just going to collect some samples, and it's running really fast, so they're all packed in there right now because I spread that out. So this is what it's seeing. It's seeing up, down, up, down, up, down, up, down, up, down. And it's nice enough to tell me way over here on the right-hand side, the frequency is 125 kilohertz. So that's really interesting. I know these EM400 cards that I'm using that run at 125 kilohertz. So that's like an RFID signal on that pin. And it's just an even one like that. So that's really cool. What happens if we put a key by it? So I'm going to time him up here, click start. And I'm going to do that again, so it's kind of slow. I've got the reader upside down, so it doesn't read as well as it reads. So that looks like the same signal. I'm going to zoom way out. Oh, there's something interesting happened. And with a little trial and error, I figured out this was the exact point at which it had read a signal and either stopped trying to read a signal or opened the lock or something. So what happened right before that? Zoom in on that. Well, that's really interesting. I'm seeing not that 125 kilohertz signal anymore. I'm seeing, if I zoom way in, this is the 125 kilohertz right here, about 125 kilohertz. So there's another signal that's kind of overlaid on top of that looks like this. Okay, time to do a little research. What does this signal mean? So look at the EM400 cards I'm using, and they use something called Manchester encoding. The way that works is you have a binary 1, it actually encodes a low-high. So binary 1 is low-high, binary 0 is high-low. And that signal that I see there matches the signal that I read. And the way I can kind of tell that is I've pretty much got bits that seem to be either 1 bit wide or 2 bits wide. And I never see anything more than 2 bits wide, and so it's really even, so that's really like that. I'm catching that signal. That's interesting. How can I, and I'm just seeing that in my scope, how can I actually do something with that? We'll get back to the protocol decoding. But how do I do something with that? Well, I can sense that high-low on the Arduino pin. I don't know if I'll be able to do much with it, but I can sense it there. So hooked it up to the Arduino. To do that, I soldered onto that pin on the board. I actually soldered on the bottom board that's going around to see that. So this is the only tool that I don't recommend going with the cheapest you find, and I would buy one of Harbor Freight tools. You get a good one that lasts a long time, it works well. So Weller's a good brand. Mine's actually that I use is from Radio Shack. It's the only thing I would probably ever buy at Radio Shack, and it's like cheap. But there's a nice one too. Most people like the Weller as well. So I soldered onto the pins. Just look at the white and the gray wire. So the white wire I've got soldered onto pin 16. The gray wire is onto a ground pin. The other two was for kind of as I went along. I was trying to get also some power off the board and things like that. Another little bit of things you need to jump into as you're getting into this hardware hacking is thinking more in binary. This was also a shift for me. It's been a long time since I had to think in binary. But Arduino makes it nice because you've got this notation where for a byte, 8 bits of ones and zeros, you can do B11111100. So you actually see on the screen what that byte is. But you also got to think in hex because a lot of your output will be printing in hex. And so that 111100 is hex FC. The first 4 bytes correspond to the F. The second 4 bytes correspond to the C. So don't be afraid of binary and hex. Just kind of get used to it a little bit to get started. The other thing, as I was trying to do some work with this on the Arduino, was really had to pay a lot of attention to data types because there's not a lot of space on that Arduino, and I'm trying to catch a big signal and then decode it. And so, I had to make sure I was using all the memory very efficiently, which again was going to be I was coding in Perl and Python. It's like unlimited, whatever you need. And I used a lot of byte arrays, so that was kind of the things. So how did I turn that signal that the board got into something interesting? Well, the way I decided to do it was I know that the Arduino has a certain, it's very much a solid, consistent processing. It doesn't have at least I'm not using interrupts to go off to other things. So for the same loop, it's always going to count the same number of times. So what I did is just start a loop that reads that pin, counts, reads that pin, counts. So as we're going across the bottom here, right now the pin's high, so it starts counting high, 1, 2, 3, 4, 5, 6, 7, and the pin goes low and it stops. Okay, it's 7. I went to loop 7 times. I'm going to write 7 to a buffer, and then reset my counter. Now it's low, 1, 2, 3, 4, 5, 6, 7, 8. Oh, it went high. So I'm going to write 8 to my buffer, reset my counter, and I just did that. So I had a buffer with basically how many times did the Arduino do that loop before the state changed. And what I got out of that was this count you see on the bottom. So it counted 73 loops, then the state changed, 0 loops, the state changed, 1 loop, the state changed. So those zeros and ones, I don't know if you noticed when we stretched out that signal, there was a little bit of 125 kilohertz in between the next signal. So I just ignore that. I'm really looking for the long ones that are like 70 or 120. But I still think I'm on the right track here because I'm seeing 70, 50, 130. So it's like X and 2X. I'm seeing signals that are this wide and signals that are twice that wide, and then some quick ones in between. So it seems like I'm on the right path. The Arduino right now is just shipping this out to the serial port, and I'm capturing it in a text editor and doing a little bit, working with it there. But once I got that, okay, how do I convert that into something meaningful again? And so the way I did that was I just wrote a loop on the Arduino that if it sees between 50 and 70 counts before the state change, that's a 1. If it sees, well, it knows whether it's a 1 or a 0. I was kind of tracking that. I started with a 1. So depending on where it's in the buffer, I know if it's a 1 or 0. But if it sees 70, it says, okay, that's just 1 byte. If it sees 120, 140, okay, that was 2 bytes. So it writes 1, 0, 0, 1, 0, and it just makes a new buffer stream like that. And that's what that ends up looking like. Actually, I can ship that down to the serial port, but it still seems like I'm on the right trail because my Manchester encoding should always be 1, 0 or 0, 1, and that's what I see here. It's 1, 0, 1, 0, 0, 1. I never see 3 of the same 1 or 0 together. So, looking good on the right path. This is kind of the size of the buffer that I could store on the Arduino before it kind of ran out of memory. And then we just need to decode that. The way we do that, again, is a 1, 0 is a 1, a 0, 1 is a 1, a 0, 1 is a 1. So we'll go do that. So then we get this string of just 1s and 0s again, but it's the real signal. It represents what's on the key. Convert that into, I think it's 40, I don't know how many bytes it is overall for the key, I forget. But there's a really nice layout of the protocol somewhere on the web I found. It starts with 9 1s, which is nice. So I just need to look in my buffer for someplace that has 9 1s. Find that 9 1s, okay, that could be the start of a key. The next 1, 2, 3, 4 bytes are a version number, first half version number. There's parity that's there. So it's the math here to figure out, okay, this blue block in the middle is actually my data that I'm looking for. And I do some parity checks and all that, but it's basically just a little more math to figure out from that string of 1s and 0s. What do I got? And so we'll show the end result here. Okay, why did that happen? So, and I've got my Arduino code says starting when it's working, which is nice, and then when I scan a badge, it saw the number 1872006, which is the same number printed on the outside of the key. So that was pretty cool. So the next thing is, well, what can I do with that? Now that I know that number. So I want to make a cloner. I want to put that number, I've stolen that number from someone else. I need to make a copy of that key. This was out of my realm, but luckily other people have done it. This guy, he's smarter about that, I can't believe his name out there, had a really good write-up of the circuit he had built to do it, which I more or less copied. And here I got a little more, kind of understanding of how the key works. If you look at the key on the inside, I've got a picture of it there. You got the coil, that's the conductor, the coil of wire. So, and then somewhere in that little board in the middle, they've got a capacitor and the other logic. on the actual key that came with the lock. And so I learned that to do this tuned circuit, 205 kilohertz, you need an inductor, and then you need a capacitor that matches to, that they resonate at 125 kilohertz. I bought one, this little one you see down at the bottom off of a website called Coilcraft. So I can do that. That's just a picture. Oh, that's not good. Just to see a picture. Okay. But so they sell these little Rfid transponder coils, just a little inductor, and they actually tell you which capacitor to match for that. And they tell you things like read distance here too. And these are made for like tires on cars, the air pressure sensor and things like that. So I thought this would be great, like a foot away they're saying. But what I found out when I built it with theirs was that I had to be touching the reader even then. It was just kind of working. And then this is a picture of that little car they have small. I don't know what I was doing wrong. It works, but the signal is just so weak. It didn't really work for me. But here's a picture of the circuit we built. It's really simple. You've got the inductor and the capacitor in there to make a tuned circuit. And then you've got this transistor there that's acting as a switch that is kind of tuning and detuning that circuit. So when it gets near the reader and the reader is putting off this 125 kilohertz signal, whether that circuit that's near it is tuned or detuned, the reader picks up on it. I don't understand it much better than that. I just know that the Arduino is turning it on and off by that. And again, that transistor is like a switch, turning it on and off to create that high-low, high-low, high-low. So I built this circuit, dug around and used fritzing, which is worked well for me. I've tried a couple of the other kind of build circuit programs. Fritzing was about the easiest I found. It didn't have a very big library of components, which kind of sucked, but it was really easy for me to drop it's got three different views. It's got kind of the component view and then your schematic view, and this schematic is what their schematic view looks like, and then it's got the actual board view. So I was able to, in the component view, drop the Arduino Nano there, my transistor, my resistor, my capacitor, my inductor, connect them all together right, and then switch over to your kind of screener circuit board view, and move the wires around and stuff. So I came up with this little green circuit board you see at the bottom, and that's kind of how I went about building the board. Again, I love projects like this that's one little thing, and I learned that, and then I do the next thing and learn something new, and so this one actually got me interested in trying to figure out this PCB etching, which was hard, but not for the reasons I thought it would be. It was hard to find the right combination of parts. Got copper board off eBay, got etching off of eBay, and after trying half a dozen different types of paper, I was just doing the toner transfer method, where you print your circuit on a piece of paper in your laser printer, and then iron it onto your board, and wherever the toner gets ironed onto the board, that's going to leave the copper there when you etch it. And etch it is just chemical that dissolves the copper where the toner isn't. So after trying a lot of things, I went to a stack of Family Fun magazines that's in our laundry room, like up here, that no one's touched in like 3 years. Pulled one off, and it was perfect. It worked great. Figured out you had to have heavy toner, and actually tell the printer was using thick paper, so it would heat up the toner a lot, so a lot of it would stick and all that kind of stuff. And I showed my wife, and she's like, "You used my Family Fun magazine?" And she had like, "Isn't this cool? You used my Family Fun magazine?" So, yeah. Luckily, half of that is advertisement, so I was able to kind of laugh. But it was cool. The results certainly aren't as great as what you buy, but it worked fine for me. This board was one that I had a larger board, and I pulled it out because everything was etched except for this one. I wanted to go to bed, so I just pulled it out and left the copper on this one. And so that gives you a sense of how it looks as it's etching. It's just eating away at the copper except for where the black is, where the toner is. But I did that. Do I have a? And there's a picture of the. I can't see the circuit, but basically made that little circuit, soldered the inductor on it. Initially, I soldered on the Coilcraft inductors, like $1 each, and I bought more than one, so that was money thrown at it. And then I realized when that wasn't working well. Well, I got another inductor. It's inside this blue key probably, and I figured out how to pry these open and get into them. It's not too hard. But these work great when you get the right capacitor for them. And on the website it tells how to do that. Or I can link you to that. But you have to figure out the right capacitor to tune the circuit 1.5 kilohertz. But pop one of these open. The wires are really fine. You can't really solder to them too easily. But it's got a couple solder points next to that circuit that they've got in there. I just took a knife and kind of cut their circuit up until it wasn't working anymore, and then soldered to their solder points. It worked. So what I have here is a little Arduino Nano with that reader you just saw. I've got it connected to the mini quarter battery. And I'm going to switch over to the start this over. Alright, so if I bring this close, demo guys are in my favor today. There we go. So it read 3376140, which is not the number on the key, which is the number I programmed into the Arduino. So that's so made the spoofer. So that's other ideas on the project then. There's an EEPROM memory on there. It's very likely, I'm guessing, that the reader itself is storing like the passcodes for the reader and the other badges that are valid on that. So, another project we could do is hook up to the pins of this EEPROM memory and see if you can read the admin passcode off of it, see if you can read the other tags, and use those tags at other panels of that person. Now, I doubt that anybody is actually using these $12 RFID readers for something worthwhile and secure because they're really cheap. There's a screw on the bottom that's a regular Phillips screw. When you remove that, you get right into the panel. What I'm showing here on the screen in the demo here is a version 1.0 board. I actually bought another one. It came as a version 3.0 board, and they kind of figured that out. So they added this little push button here that the back of the panel pushes down. And while that's down, it works fine. If that button's out, it's got an alarm, beep, 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 like someone's opened the panel, which I just bypassed by soldering the points of the thing together. But you open it up, and it's like, okay, it was a screw to open it, and from there I can open the lock by bridging these pins across the relay, or a bunch of things you can do. So it's not a secure lock, and you get what you get for $12, but it's fun to play with. So that's one project idea I haven't tried yet. Hint cards. So this was a big, so nobody's really using these EM400 cards. Well, maybe they are. I don't know. I haven't come across them too much for like banks and things like that. But the hint cards that you see here on the screen are pretty popular. I've seen those a lot. And it's also 125 kilohertz. I knew that, but I know it's a different signal. And so what I would just try out was what happens if I put a hint card by my reader. We're going to go back to our logic analyzer, drop the turn on top of it, start reading. And there's a signal there, so that's interesting. If we zoom in on it, you can't see it real well on the screen, but what you end up seeing is it's not just that clean 125 kilohertz signal we had before, it's like mashed together here where it's 15 kilohertz, or stretched out here where it's 12 kilohertz. So it's really modified that signal to be mashed together, stretched out, mashed together, stretched out. And looking at the protocols for the hint card, again, looking it up on the internet, you find that it uses something called frequency shift keying, where it's just that. Zeros and ones are either stretched or compressed or whatever. So, okay, that's cool. Can I take my Arduino that's already doing this EM400 card and can I have it grab hint cards as well? So that was the next project that I went down the path on. I think that's the only slide I have on it because it was really hard to do, and I don't quite have it working yet. The bits are shorter, so you've got a lot more areas in terms of the Arduino trying to count, it only counts 9 or 10 bits before the state changes, so more errors there. What I really found was a problem, though, was the HIT card has a much longer code. It's not just the few bytes that the EM card is. So I had to create a bigger buffer to store more counts, and it's store counts. So I had to create a much bigger buffer to store more counts and try and catch that card. The standard Arduino Uno has enough memory to catch, maybe 30% more than a full card read in a buffer, but it doesn't really have enough room left for your program then in the memory. So I could either catch too short of a buffer or not have enough room for my program. The way I kind of got around that is I was able to at least fill my buffer and then just have a tiny bit of code that spits the buffer out via serial, did the decode offline, like on a Windows machine, and proved that, yeah, it can be done. I ultimately, when I was done, doing some math and all that kind of stuff, came up with the number that was on the back of the card. I said, yeah, it can be done. But my goal was to make this into like a pen testing tool. I want to take the reader itself, pack the little Arduino Nano in there, pack the board from like one of the TP-Link routers in there, and you have that serial port, have a web page, and then pack some batteries. And I was actually able to fit, the Arduino, the mini pointer board, and the and like 6 AA batteries inside one of these that I modded a little bit with this case. It's this one right here. So all inside there, I could pack all that in there, runs off the batteries, stick it to a wall, paint black, and look just like everybody else's reader. Put it right next to them, and they're going to spike both or whatever. But I couldn't get far enough where I could read. With the EM400, I could read the other Arduino, send it to the mini pointer, put it on a web page on the mini pointer, and actually see that web page, standing on the front, that type of thing. So that was cool, but I couldn't do it with HIT cards because, I could write C code on the mini pointer to do the decode. I could Perl the mini pointer, then I need 2 USB ports. So a lot of hurdles there. I don't have it working yet. It'd be cool if someone could get that far. I saw somebody else had some Arduino code out there for decoding these, but I think they were using the same signal input. But he was doing some smarter things that I was for sure, where he was actually using the timer on the Arduino to time the length of the ups or downs rather than just count them and things like that. But his code didn't work when I tried it, so I don't know what the problem was. Or you could use a more powerful Arduino board that has more memory and more hertz or whatever. But that's still out there. It can be done. You'd be very smart if you could do it. I haven't been able to do it yet. But that's what I was talking about, the mini pointer RFID, packing all that in there. Yeah, that's all I really have to talk about. Cool, yeah. This information, I've got some of it out there on minipointer.com, go to minipointer RFID. I'm going to get kind of the parts list for this stuff out there so you can do it, the schematic out there. If you're here, if you want to email me, if you really want one of these boards, I'll probably make another batch and I can mail you one, just email me. Go to minipointer.com and find my address board over there.